Welcome back, folks. It's time for our last section in Chapter 1. It's actually a combo section. We're looking at both 1.5 and 1.6. And what I've done is pulled out from these two sections the concepts that I think are most important for us. So that's why I've combined these into one. Here's the kinds of things we're going to be looking at today. Just as a quick review, if we have the limit of a function as x approaches c, if that equals, let's just say, positive or minus infinity, it tells us something about the function. We really know that this limit does not exist. So that's one of the two ideas we'll be reviewing and talking about in this section. The other idea is this: the limit of a function as x goes off towards infinity can equal some number. And I know what you're thinking right now. You're thinking to yourself, hey, Mr. S, what's the deal with this? You told us that the value of interest had to be a number. It can't be the idea of infinity. And this is, we're going to bend our rules a little bit. So over here in this limit statement, we have as x approaches c, where c is some number on the real number line that we can actually point to. Whereas over here, we're looking at the limit of the function as x goes off towards infinity. And really, in pre-calculus, I had another name for this. I called it end behavior. We looked at the end behavior of the function as we went off towards positive or negative infinity. So that's kind of the two ideas that we're wrapping up in this section. So let's just look at question number 1. Determine the following limit. The limit of x divided by x minus 5 as x goes off towards 5. And we can clearly see in the graph that we have behavior going off towards negative infinity here and off towards positive infinity here. So if I were to write that limit statement, it would look something like this. So the limit of f of x as x approaches 5 from the left. So as we approach x equals 5 from the left, this goes off towards negative infinity. And really, we know that that means the limit does not exist. Now let me look at it from the right-hand side. So as we approach x equals 5 from the right-hand side, we go off towards positive infinity. And again, we know that this limit does not exist. So this right here, because the limit does not exist from the left and the right. Okay, guys, calm down, calm down. We know that the overall limit does not exist. And that kind of leads me to an important idea that I want to capture down here in the gray box. So the idea that I want to capture here is this. You know, the limit from the left and the right here goes off towards infinity, and we know that that means, you know, visually we can see that in the graph. As x approaches, at x equals 5, we have a vertical asymptote, and that's the big idea here. X equals c is a vertical asymptote. So x equals c is a vertical asymptote of the graph of y equals f of x if the following things are true. Okay, so if the limit as x approaches c from the left is equal to plus or minus infinity, and the limit of f of x as x approaches c from the right equals plus or minus infinity, then we have a vertical asymptote at x equals c. Okay, that's big idea number 1 for this section. Let's move on to big idea number 2, and we're going to look at that with an example. So I have a limit statement here. It says determine the limit of this rational function. I've got a quadratic, 3-term quadratic trinomial in the numerator, and I have a 2-term quadratic in the denominator, a quadratic binomial, and I'm looking for the limit of that as x goes off towards infinity. Now, there's a hint here. First of all, this is the first time we've looked at any limit where the value of interest is infinite. So we're trying to figure out what happens to this function at the ends of the number line, at the right end of the number line as x goes off towards positive infinity. And there's a little hint here. It says, what can we ignore for this limit? So what I'd like you to think about is this right here. That term right there, those two terms, the minus 3x plus 7 in the numerator and the plus 8x in the denominator. As x goes off towards infinity, these terms are insignificant. So another way to think of that is the 3x squared term grows much faster as x goes towards infinity than minus 3x plus 7. And that's because the quadratic grows a lot faster than the linear or the constant term. In fact, the constant term, plus 7, doesn't grow at all. Think of the same idea in the denominator. The x squared grows much faster than the 8x. So we can really ignore those terms. And that's going to give us a problem that looks like this. Folks, you may notice that I spend a lot of time rewriting the original problem, and that's of value because I want to be very specific with my notation and make sure that you understand exactly where we start and where we're going to. So I would encourage you to do the same. It's just good mathematical practice. So the limit of this rational function as x goes off towards infinity is going to be equal to the limit of this function as x goes off towards infinity. And the reason for that is because those insignificant terms I can ignore as x goes off towards infinity. Well, now I just look at 3x squared divided by x squared, and that simplifies to just plain old 3. So this limit is 3. And that is an idea that we have talked about in pre-calculus. We didn't call it a limit. We just looked at end behavior of a function. In fact, these 3 rules right here are, I have stolen these from pre-calculus and just modified them to say, talk about the limit as x goes off towards infinity. So we're going to look for, these rules are for limits as x goes to infinity of rational functions. And the key that you need to think about here, okay, quit jumping around on me. What you need to do is you need to look for the highest power. Okay, so if the highest power is in the numerator, the limit of the function as x goes off towards infinity is going to be plus or minus infinity, which means the limit does not exist. Another way to say that is, we'll say that the function grows without bound. So it keeps growing and growing and growing without bound. Now I'm showing you all these special cases of limits with rational functions where the infinite piece right there is a positive infinity. The same is true for negative infinity. So I didn't want to have to rewrite that a separate time. Just know that it same holds true for negative infinity. Okay, so let's look at the next bullet here. If the highest power is in the denominator, then the limit of the function as x goes off towards infinity is, well, that's going to be 0, because if the denominator grows faster than the numerator, we approach 0. And this is going to give us a horizontal asymptote of y equals 0. And that horizontal asymptote of y equals 0 is really the x-axis. Okay, let's look at the last one. What if both the numerator and the denominator have the same exponent? They're both, the powers are equal. Well, then the limit of the function as x goes off towards infinity is going to be the ratio of the coefficients on the highest powers. That will give us a horizontal asymptote of y equals whatever that ratio is. All right, folks, this again is something that you have seen in pre-calculus. What are we doing now? Well, we're now looking at it as a limit as x goes off towards infinity, rather than just saying, hey, what's the end behavior of the function? Okay, so these rules seem really easy, but it's not quite that easy. There are some special things you have to keep in mind, and really you just have to be smart about functions, and you have to know how functions behave. So each of these 2 examples gives us some special things we need to consider. So let's look at the first example. So this is a limit of a rational function where the numerator is a 5th degree polynomial, and that happens to be the highest power in the function. So it's a rational function where the numerator is a 5th degree polynomial and the denominator is a 4th degree polynomial. But I am going to make one note here. Even though we have x going off towards negative infinity, 9 times x to the 4th will always be positive. Why is that? Because x to the 4th is positive regardless of what the input is, positive or negative. Okay, so I kind of have to think about this in 2 parts. My denominator is always positive as x goes off towards a negative infinity. And remember, you might say, well, what about these other terms here? Well, all of these terms here do not affect the limit or the value of the function as x goes off towards negative infinity. I shouldn't say they don't affect it. They have minimal effect. In fact, the effect is so small we can ignore it. Same idea up here. We can ignore these as x goes off towards negative infinity because the highest power dominates. Okay, so let's take a look back at that numerator again. If x is less than 0, what can we say about negative 2x to the 5th power? Well, let's see. X to the 5th, that's an odd exponent, so it's going to maintain the sign of the input. The sign of the input will be negative, so x to the 5th will be negative, but we're multiplying that by negative 2. So as x goes off towards negative infinity, negative 2x to the 5th is greater than 0. So I have a positive numerator, I have a positive denominator. What does that tell me about the whole function? So as x goes off towards negative infinity, the limit of the function will be a positive numerator divided by a positive denominator, but the highest power is in that numerator. If I look back up at my rules, if it's in the numerator, if the highest power is in the numerator, well, then we go off towards positive or negative infinity. In this case, it'll be positive because we're dividing a positive number by a positive number. So this is positive infinity. And remember, that truly means that the limit does not exist, but we're just telling you that it's positive infinity, so you have some idea about behavior of the function. All right, let's go on to part B here. The limit as x approaches negative infinity of, well, I have another rational function here, but the numerator's got a square root in it, and square roots always complicate things. So let's take a look first. Is there any terms here we can ignore as x gets really large, or in this case really small as it goes to the left? Well, we can ignore that, and we can ignore that. So this limit is really the same as the limit of the square root of x squared over 2x. So I'm really looking for that limit. And it's now time to talk about the square root of x squared. Somebody that doesn't remember a lot about algebra might say that the square root of x squared, oh, that's easy. The square root symbol just erases the exponent, and it just equals x, and that is completely false. The square root of x squared does not equal x. The square root of x squared equals the absolute value of x. Okay, so we have to remember that. That means the numerator will always return a positive value. Even though we're looking at the limit as x goes towards negative infinity, that numerator will always be positive. Now the denominator, 2x, well, that'll be the sign of whatever the input is, so that'll be negative. So now we have the following. The limit of the square root of x squared over 2x as x goes off towards negative infinity is equal to the limit x goes towards negative infinity of the absolute value of x over 2x, and that will equal negative 1/2. Why is it negative? Because we have a negative input in the denominator that stays negative, but the numerator will turn positive. Bang, final answer. All right, folks, congratulations. You made it through the first page of the notes here. We're going to jump over to the second page in a fresh video.